Tonight, we're going to journey through the complete story of galaxies, those magnificent island universes that contain everything we know and everything we might ever discover. From their violent births in the early universe to their eventual fates trillions of years from now, we'll explore these cosmic cities of stars in all their variety and splendour. Settling comfortably, let your breathing slow, and allow your mind to drift among these vast stellar metropolises as we trace their epic saga from the first moments after the Big Bang to the far distant future when the last stars fade to darkness. The story of galaxies begins not with light, but with darkness. In those first moments after the Big Bang, 13.8 billion years ago, the universe was a place unlike anything we can truly imagine. There were no stars yet, no planets, no vast spiral arms spinning through space. Instead, there was a hot, dense soup of particles and radiation, so intense that light itself couldn't travel freely through it. For nearly 400,000 years, the cosmos remained opaque, a glowing fog of hydrogen and helium atoms just beginning to form as the expanding universe cooled from its initial, unimaginable temperatures. As this primordial fog cleared and the universe became transparent for the first time, gravity began its patient work. The matter in the universe wasn't perfectly smooth, thankfully for us. There were tiny variations in density, regions where matter was just slightly more concentrated than in others. These minuscule differences, no more than 1 part in 100,000, would become the seeds of everything we see in the cosmos today. Like raindrops forming around specks of dust in a cloud, matter began to gather around these denser regions, pulled together by gravity's invisible threads. During this era, which astronomers call the cosmic dark ages, the universe was a very different place from what we observe today. There was matter, certainly, mostly hydrogen with a touch of helium and barely detectable traces of lithium, but there was no light except for the fading glow of the Big Bang itself, stretching and cooling as the universe expanded. For perhaps 100 million years, this darkness persisted, a cosmic intermission between the brilliant beginning and the star-filled universe we know today. But even in this darkness, construction was underway. Dark matter, that mysterious substance that makes up about 85% of all matter in the universe, was already forming vast, invisible scaffolding. We cannot see dark matter directly, we can only detect its gravitational influence, but it was dark matter that provided the framework around which normal matter would gather. These dark matter halos, as astronomers call them, were the construction sites where the first galaxies would eventually form. The process was gradual at first, almost imperceptibly slow by human standards. Hydrogen gas flowed along invisible dark matter filaments, streaming into growing wells of gravity. As more matter accumulated, these regions became denser and denser. The gas clouds grew larger, their own gravity pulling in more material from the surrounding space. Within these clouds, even denser pockets formed, regions where the gas became so compressed that something extraordinary was about to happen. When we think about the formation of the very first stars, we need to adjust our expectations based on what we see in the universe today. These weren't like the stars being born in our modern Milky Way. The first stars, sometimes called population 3 stars, were monsters. Without any heavy elements to help cool the collapsing gas clouds, these primordial stars could only form when enormous amounts of hydrogen gathered together. They were probably hundreds of times more massive than our Sun, burning with a fierce blue-white light that would have been visible across vast cosmic distances if anyone had been there to see them. These massive first stars lived fast and died young. While our Sun will shine steadily for 10 billion years, these primordial giants exhausted their nuclear fuel in just a few million years. But their brief lives were tremendously important for the story of galaxies. When they died in spectacular supernova explosions, they did something that had never happened before in the universe. They created and dispersed the first heavy elements. Carbon, oxygen, nitrogen, iron, all the elements that would eventually make planets and life possible were forged in the nuclear furnaces of these massive stars and blown out into space when they exploded. This process of stellar death and rebirth began to transform the universe. Each generation of stars enriched the cosmos with more heavy elements, which astronomers call metals, even though many of them aren't metallic in the conventional sense. These metals changed everything about how future stars would form. They provided new ways for gas clouds to cool and collapse, allowing smaller stars to form. They created dust grains that would eventually clump together to form planets. They laid the groundwork for the complex chemistry that would eventually lead to life. As more and more stars formed and died, the first recognizable galaxies began to take shape. These early galaxies were not the majestic spirals or massive ellipticals we see today. They were smaller, more irregular, often just collections of young stars and gas clouds bound together by gravity. Through our most powerful telescopes, when we look at the most distant galaxies, we're seeing these cosmic infants, catching them in the act of assembly billions of years ago. The James Webb Space Telescope has revolutionized our understanding of these early galaxies, revealing surprises that have forced astronomers to reconsider their models. Some of these ancient galaxies appear to be more massive and more mature than expected, suggesting that galaxy formation might have proceeded more rapidly than previously thought. We're seeing galaxies that existed when the universe was only a few 100 million years old, already containing billions of stars and showing signs of complex structure. These early galaxies were sites of furious star formation. Astronomers call them starburst galaxies, and they were converting gas into stars at rates that dwarf anything we see in most galaxies today. Where the Milky Way forms perhaps 1 or 2 new stars per year, these early galaxies were forming hundreds or even thousands of stars annually. The universe was experiencing its peak era of star formation, a cosmic boom time when stars were being created faster than at any other period in cosmic history. But this frenetic pace couldn't last forever. Star formation requires raw material, specifically cold gas that can collapse under its own gravity. As stars formed, and especially as they died in supernova explosions, they heated and dispersed the surrounding gas. Some gas was blown completely out of smaller galaxies, lost to intergalactic space. Other gas was heated to such high temperatures that it could no longer collapse to form new stars. Gradually, the rate of star formation began to decline. This decline wasn't uniform across all galaxies. Larger galaxies, with their stronger gravitational fields, could hold on to their gas more effectively. They could also pull in fresh gas from their surroundings, maintaining their star formation for longer periods. Smaller galaxies, particularly those orbiting larger ones, often had their gas stripped away by gravitational interactions or by ramming through the hot gas that fills galaxy clusters. As we observe galaxies throughout cosmic history, we see this gradual transition from a universe dominated by young, blue, actively star-forming galaxies to one increasingly populated by older, redder, more sedate galaxies. Astronomers sometimes call this transition galaxy quenching, the process by which galaxies stop forming new stars and begin to age quietly. Understanding exactly how and why galaxies quench their star formation is one of the major challenges in modern astronomy. The story becomes even more complex when we consider that galaxies don't evolve in isolation. From very early in cosmic history, galaxies have been interacting with each other, sometimes dramatically. Galaxy collisions and mergers have played a crucial role in shaping the galaxy population we see today. When 2 galaxies come together, the result can be spectacular, triggering bursts of star formation, feeding supermassive black holes and completely restructuring the galaxies involved. These interactions were much more common in the early universe, when galaxies were closer together and moving more slowly relative to each other. Through computer simulations and observations of colliding galaxies at various distances and therefore various times in cosmic history, astronomers have pieced together how these cosmic train wrecks unfold. The process is usually slow by human standards, taking hundreds of millions of years, but it can completely transform the galaxies involved. When two spiral galaxies of similar size collide, they often merge to form an elliptical galaxy. The ordered rotation of the spirals is disrupted, leaving a more chaotic football-shaped collection of stars. The gas in the galaxies can be compressed by the collision, triggering intense bursts of star formation. These merger-triggered starbursts can be so intense that they use up most of the available gas in just a few 100 million years, leaving behind a galaxy with little fuel for future star formation. Not all galaxy interactions result in mergers. Sometimes galaxies pass close to each other, distorting each other's shapes through gravitational tides, but ultimately continuing on their separate ways. These interactions can create spectacular features like tidal tails, long streams of stars, and gas pulled out of galaxies by gravitational forces. The antennae galaxies visible in the constellation Corvus show this process in action, with two long tails of material extending far from the colliding galaxy cores. Even our own Milky Way bears the scars of past interactions and ongoing minor mergers. Streams of stars in our galaxy's halo mark the remains of smaller galaxies that have been torn apart and absorbed over billions of years. The process continues today. The Sagittarius dwarf galaxy is currently being disrupted and absorbed by the Milky Way, its stars being scattered across our sky in a stream that wraps around our galaxy multiple times. Looking ahead, our galaxy faces a dramatic future interaction. The Andromeda Galaxy, our nearest large galactic neighbour, is heading toward us at about 110 kilometers per second. In approximately 4.5 billion years, these two spiral giants will begin their cosmic dance, eventually merging to form a single, larger elliptical galaxy that some astronomers have already nicknamed Milkomeda or Milkdromeda. This future merger illustrates an important point about galaxy collisions. Despite containing hundreds of billions of stars each, the Milky Way and Andromeda will merge without any direct stellar collisions. Stars are simply too small and too far apart for collisions to occur. Instead, the galaxies will pass through each other, their gravitational fields gradually reorganizing the stars into a new configuration. Any planets orbiting those stars will likely continue unaffected, though their night skies will change dramatically over the course of the merger. The role of supermassive black holes in galaxy evolution adds another layer to this complex story. Nearly every large galaxy harbours a supermassive black hole at its centre, ranging from millions to billions of times the mass of our Sun. These cosmic monsters play a surprisingly important role in regulating their host galaxies, despite being tiny compared to the galaxy as a whole. The supermassive black hole in the Milky Way, called Sagittarius A star, contains about 4 million solar masses, impressive, but still only about 1/10,000th of a percent of our galaxy's total mass. When supermassive black holes actively feed on surrounding gas and dust, they can become some of the most luminous objects in the universe. These active galactic nuclei can outshine all the stars in their host galaxy combined. The energy and radiation they produce can heat and expel gas from the galaxy, shutting down star formation. This feedback mechanism helps explain why the most massive galaxies tend to have very little ongoing star formation. Their central black holes have essentially turned off the tap, preventing gas from cooling and forming new stars. The relationship between galaxies and their central black holes appears to be fundamental. There's a remarkably tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole, suggesting that galaxies and their black holes evolve together. How this coordinated growth happens remains one of the key questions in galaxy evolution. Did the black holes form first and help build their galaxies around them? Did galaxies form first and then grow their central black holes? Or did both processes happen simultaneously, with galaxies and black holes regulating each other's growth through complex feedback mechanisms? Spiral galaxies represent perhaps the most visually stunning class of galaxies in our universe, their graceful arms sweeping through space like cosmic pinwheels. When we look at a spiral galaxy face-on, we're seeing one of nature's most beautiful patterns, a structure that emerges from the complex interplay of gravity, rotation, and star formation. About 60% of all galaxies in the local universe are spirals, including our own Milky Way, making them crucial to understanding how galaxies function and evolve. The basic structure of a spiral galaxy consists of several distinct components, each playing a vital role in the galaxy's appearance and behavior. At the center lies the bulge, a roughly spherical concentration of generally older, redder stars. Surrounding this bulge and extending far into space is the disk, a flat, rotating collection of stars, gas, and dust, where the spiral arms reside. Beyond the visible disk, extending much farther into space, is the halo, a roughly spherical region containing old stars, globular clusters, and vast amounts of dark matter. The disk is where the action happens in a spiral galaxy. It's here that we find the spiral arms, those beautiful patterns that give these galaxies their name. But the spiral arms are not what they might first appear to be. They're not material structures in the sense that the same stars always make up an arm. Instead, they're density waves, regions where stars and gas are temporarily more concentrated as they orbit around the galaxy's centre. Think of the spiral arms like a traffic jam on a circular highway. The location of the traffic jam, the slowdown zone, remains relatively fixed, but the individual cars, or in this case stars, move through it. As stars approach a spiral arm in their orbit around the galaxy, they slow down slightly and bunch up, creating the appearance of a bright arm. After passing through, they speed up again and spread out, continuing their journey around the galaxy until they encounter the next arm. This density wave theory, developed in the 1960s by Chinese-American astronomers C.C. Lin and Frank Hsu, explains many features of spiral galaxies that would otherwise be puzzling. It explains why spiral arms don't wind up over time, which they would if they were material structures rotating with the galaxy. It also explains why we see different types of objects concentrated in different parts of the arms. As gas clouds orbit the galaxy and encounter a spiral arm, they experience compression. This compression can trigger the collapse of gas clouds, leading to the formation of new stars. The most massive of these new stars are extremely bright and blue, but they also have very short lifetimes, just a few million years. By the time these massive stars have moved very far from where they were born, they've already exhausted their fuel and died. This is why we see bright blue stars concentrated along the spiral arms. They simply don't live long enough to travel far from their birthplaces. The spiral arms are therefore outlined by these short-lived brilliant blue stars and by the glowing gas clouds where new stars are being born. The reddish-pink glow we see in many spiral galaxy images comes from hydrogen gas heated by the ultraviolet radiation from nearby hot young stars. These HI regions, as astronomers call them, are stellar nurseries where the next generation of stars is taking shape. Between the spiral arms, in what astronomers call the inter-arm regions, the scene is quite different. Here we find older stars that have had time to drift away from their birthplaces. The star formation rate is lower, and the stellar population is dominated by smaller, longer-lived stars like our Sun. Our solar system currently resides in just such a region, between the Perseus and Sagittarius arms of the Milky Way, in a minor feature sometimes called the Orion spur, or local arm. The number and shape of spiral arms vary considerably among galaxies. Some galaxies have two prominent, well-defined arms that can be traced for nearly a full rotation around the galaxy. These grand design spirals, as they're called, include famous examples like the Whirlpool Galaxy, M51 and MAE1 in Ursa Major. Other galaxies have multiple arms, sometimes 4 or more, that may be less well defined or more fragmented. Still others, called flocculent spirals, have a patchy cotton-like appearance with many short spiral segments rather than continuous arms. What determines the spiral pattern in a particular galaxy is still not completely understood. Grand design spirals often have a companion galaxy nearby, suggesting that gravitational interactions might help organize and maintain clear spiral patterns. The beautiful Whirlpool Galaxy, for instance, has a smaller companion galaxy, NGC 5195, that appears to be interacting with one of its spiral arms. Computer simulations suggest that such interactions can indeed trigger and maintain strong spiral patterns. The rotation of spiral galaxies reveals one of the great mysteries of modern astronomy. When astronomers measure how fast stars orbit around spiral galaxies at different distances from the centre, they find something unexpected. Based on the visible matter in galaxies, stars in the outer regions should be orbiting much more slowly than those closer to the centre, just as planets farther from the Sun orbit more slowly than inner planets. But that's not what we observe. Instead, the orbital speeds remain roughly constant or even increase slightly in the outer regions of galaxies. This flat rotation curve, as it's called, implies that there's much more matter in galaxies than we can see. This invisible matter, dark matter, appears to be distributed in a vast halo surrounding the visible galaxy. In fact, observations suggest that spiral galaxies contain about 5 to 10 times more dark matter than normal matter. The presence of all this dark matter has profound implications for how spiral galaxies maintain their structure. The additional gravity from dark matter helps stabilize the disk against various instabilities that might otherwise tear it apart. It also affects how spiral density waves propagate through the disk and may influence the number and shape of spiral arms. The disks of spiral galaxies are remarkably thin compared to their diameters. The Milky Way's disk, for example, is about 100,000 light-years across, but only about 1,000 light-years thick in the solar neighbourhood. That's a ratio of about 100 to 1, proportionally thinner than a sheet of paper. This thinness is maintained by the rotation of the galaxy, which provides centrifugal support against gravity in the plane of the disk, while there's no such support in the vertical direction. But spiral galaxy disks are not perfectly flat. Many show various forms of warping, especially in their outer regions. The Milky Way's disk, for instance, is warped like a potato chip or a vinyl record left in the sun. One side of the outer disk curves above the main plane, while the opposite side curves below. These warps might be caused by gravitational interactions with satellite galaxies, or by the infall of intergalactic gas with different angular momentum than the disk. The gas content of spiral galaxies is crucial to their continued vitality. While elliptical galaxies have used up or lost most of their gas, spirals retain substantial gas reserves, typically about 10 to 15% of their total normal matter mass. This gas is primarily hydrogen, both in atomic form in the outer disk and molecular form in the inner regions and spiral arms. It's this gas that fuels ongoing star formation, allowing spiral galaxies to maintain their blue, youthful appearance over billions of years. The distribution of gas in spiral galaxies follows interesting patterns. Atomic hydrogen typically extends well beyond the visible stellar disk, sometimes to twice the optical radius or more. This extended gas disk represents a reservoir of future star-forming material. As gas flows inward or is compressed by spiral density waves, it can transition from atomic to molecular form, creating the giant molecular clouds where stars are born. Radio observations have revealed that many spiral galaxies have holes or bubbles in their gas distribution. These structures are created by stellar feedback, the combined effects of stellar winds and supernova explosions from massive stars. When multiple massive stars form in the same region, their combined energy output can blow a bubble in the surrounding gas, sometimes breaking completely through the thin disk and venting hot gas into the halo. This process helps regulate star formation by disrupting nearby gas clouds and potentially triggering or suppressing star formation in adjacent regions. The chemical composition of spiral galaxies shows interesting gradients from center to edge. Generally, the inner regions have higher concentrations of heavy elements, what astronomers call higher metallicity, while the outer regions are more metal poor. This gradient arises because star formation has typically proceeded for longer and at higher rates in the denser inner regions, leading to more generations of stellar enrichment. Understanding these abundance gradients helps astronomers piece together the formation history of galaxies and test models of galaxy evolution. The central regions of spiral galaxies often show distinct structures beyond just the central bulge. Many spirals have a bar, an elongated structure of stars extending from the center through the inner disk. About 2/3 of spiral galaxies are barred spirals, including our own Milky Way. These bars play important roles in galaxy evolution, funneling gas toward the center where it can fuel star formation or feed the central, supermassive black hole. Bars appear to be rotating rigid structures, like a spinning rod, rather than following the differential rotation of the disk. This creates interesting dynamics at the ends of the bar, where the bar pattern speed matches the orbital speed of stars and gas. These locations, called corrotation resonances, are often where the spiral arms begin, emerging from the ends of the bar and winding outward through the disk. The formation and evolution of bars is still an active area of research. Bars can form spontaneously in galaxy disks through gravitational instabilities, but they can also be triggered by interactions with other galaxies. Once formed, bars can be long-lived structures, persisting for billions of years. However, they can also be destroyed by various processes, including the infall of gas that changes the orbital structure of the inner galaxy, or interactions with massive companions. Some spiral galaxies show ring structures, in addition to or instead of clear spiral arms. These rings often occur at specific resonance radii, where the gravitational influence of a bar creates special orbital conditions. Inner rings typically encircle the bar, while outer rings can extend to the edge of the optical disk. These ringed galaxies provide important tests of our understanding of galactic dynamics and the role of resonances in shaping galaxy structure. The vertical structure of spiral galaxy disks reveals multiple stellar populations with different characteristics. Close to the midplane of the disk, we find the youngest stars and most of the gas and dust. This thin disk component is where active star formation occurs. Above and below this thin disk is a thicker disk component containing older stars. These thick disk stars have larger random motions, causing them to oscillate farther from the midplane as they orbit the galaxy. The origin of thick disks is debated among astronomers. They might form through the heating of a pre-existing thin disk by gravitational interactions with satellite galaxies or massive gas clouds. Alternatively, they might be the remnants of an early, more turbulent phase of disk formation when the galaxy was younger. Some evidence suggests that thick disks formed relatively early in galaxy history, perhaps in the first few billion years, and have been relatively stable since then. Star formation in spiral galaxies follows interesting patterns and cycles. It's not a smooth, continuous process, but rather occurs in bursts and waves. Individual regions might experience intense star formation for a few million years, then become quiet for much longer periods. This episodic nature of star formation is driven by the complex interplay of gas accumulation, compression by spiral arms or other processes, stellar feedback, and gas depletion. On larger scales, spiral galaxies can experience galaxy-wide bursts of star formation triggered by interactions with other galaxies or the infall of fresh gas. These starbursts can temporarily increase the galaxy's star formation rate by factors of 10 or more. However, such intense activity typically can't be sustained for long, usually lasting only a few 100 million years before the gas is exhausted or expelled. The future evolution of spiral galaxies depends on their environment and interactions. Isolated spirals can maintain their structure and continue forming stars at a modest rate for many billions of years, as long as they can retain or acquire gas. However, most spirals will eventually experience major interactions that transform their structure. In galaxy clusters, spirals can have their gas stripped away by ram pressure as they move through the hot intracluster medium, transforming them into gas-poor lenticular galaxies. Elliptical galaxies represent the titans of the galactic realm, massive accumulations of stars that can contain trillions of suns and extend across hundreds of thousands of light years. Unlike the dynamic star-forming spiral galaxies with their beautiful patterns and ongoing activity, ellipticals are generally quiet, settled systems dominated by old stars following randomized orbits. They are the retired giants of the cosmos, their days of vigorous star formation long behind them, now aging gracefully in cosmic retirement homes. The name elliptical comes from their appearance, which ranges from nearly spherical to quite elongated, like an American football. Edwin Hubble classified them with a simple scheme, E0 for nearly round galaxies, through E7 for the most elongated ones. But this two-dimensional appearance can be deceiving. A galaxy that appears round might actually be football-shaped, but oriented with its long axis pointing toward us. Conversely, an apparently flattened galaxy might be more spherical, but viewed edge-on. Determining the true three-dimensional shapes of elliptical galaxies requires careful analysis of their stellar motions and detailed modelling. The stellar populations in elliptical galaxies tell a story of ancient history. When astronomers analyse the light from these galaxies, breaking it down into its component colours and spectral lines, they find evidence of predominantly old stars, typically 10 billion years or more in age. These stars formed when the universe was young, in great bursts of activity that converted vast reservoirs of gas into stars over relatively short periods. The reddish colour of elliptical galaxies comes from these aging stars, as the hot, blue, massive stars that once blazed brightly have long since exhausted their fuel and died, leaving behind the cooler, redder, lower mass stars that can shine for billions of years. The formation of elliptical galaxies has been one of the great puzzles in astronomy. For many years, astronomers debated two main scenarios. In the monolithic collapse model, ellipticals formed early in the universe's history through the rapid collapse of massive gas clouds. This collapse would trigger an intense burst of star formation, converting most of the gas into stars within a billion years or so. The alternative hierarchical model suggests that ellipticals formed more gradually through the merger of smaller galaxies, particularly spiral galaxies. Modern observations have largely favoured a hierarchical formation scenario, though with important nuances. When we look at distant elliptical galaxies, seeing them as they were billions of years ago, we find that massive ellipticals were already in place when the universe was only a few billion years old. However, detailed studies of nearby ellipticals reveal evidence of past mergers and ongoing assembly. Many ellipticals show faint shells or streams of stars in their outer regions, the ghostly remains of smaller galaxies that have been absorbed over cosmic time. The internal dynamics of elliptical galaxies differ fundamentally from those of spirals. While spiral galaxies are supported by organized rotation, with most stars orbiting in the same direction in a flat disk, elliptical galaxies are supported by random stellar motions. Stars in ellipticals follow complex, often chaotic orbits that take them on looping paths through the galaxy. Some stars plunge through the dense central regions, then swing out to the sparse outer reaches before falling back again. Others follow more circular paths, but oriented in every possible direction. This difference in dynamics has profound implications for the structure and evolution of ellipticals. Without organized rotation to flatten them into disks, ellipticals maintain their three-dimensional shapes through the balance of random stellar motions against gravity. The velocity dispersion, a measure of how fast stars are moving in random directions, increases toward the center of the galaxy where gravity is strongest. This relationship between velocity dispersion and gravitational potential provides astronomers with a way to measure the mass distribution in elliptical galaxies, including the invisible dark matter. One of the most remarkable discoveries about elliptical galaxies is the fundamental relationships that connect their various properties. The Faber-Jackson relation discovered in the 1970s shows that more luminous elliptical galaxies have higher velocity dispersions. There's also a relationship between size and luminosity, and another between surface brightness and size. These relationships combine into what astronomers call the fundamental plane, a tight correlation between size, surface brightness, and velocity dispersion that all ellipticals follow. The existence of the fundamental plane tells us that elliptical galaxies are not random collections of stars, but follow regular scaling laws. These relationships likely reflect the physics of galaxy formation and the role of dark matter. They also provide powerful tools for astronomers, allowing them to estimate distances to elliptical galaxies and track their evolution over cosmic time. At the centers of massive elliptical galaxies lurk some of the most massive black holes known in the universe. While the Milky Way's central black hole weighs in at about 4 million solar masses, the black holes in giant ellipticals can exceed 10 billion solar masses. The elliptical galaxy M87, famous for the first image ever taken of a black hole's event horizon, harbours a black hole of about 6.5 billion solar masses. The relationship between elliptical galaxies and their central black holes is remarkably tight. The mass of the black hole correlates strongly with the velocity dispersion of stars in the galaxy's central regions, a relationship known as the M-sigma relation. This correlation suggests that galaxies and their black holes grow together, regulated by feedback processes. When the black hole feeds actively, it can release enormous amounts of energy that heat and expel gas from the galaxy, shutting down both star formation and further black hole growth. Giant elliptical galaxies are typically found at the centers of galaxy clusters, where they reign as the dominant galaxies. These brightest cluster galaxies, or BCGs, are among the most massive galaxies in the universe, sometimes containing several trillion stars. They sit at the bottom of the cluster's gravitational potential well, where they can grow by absorbing smaller galaxies that fall toward the cluster center. The growth of these giant ellipticals, through galactic cannibalism is an ongoing process we can observe today. In many clusters, we see evidence of recent or ongoing mergers, with disturbed galaxies, tidal streams, and multiple nuclei indicating galaxies in the process of combining. Computer simulations suggest that a typical giant elliptical might have absorbed dozens of smaller galaxies over its lifetime, growing steadily more massive through cosmic time. But not all elliptical galaxies are giants. Dwarf ellipticals are actually the most common type of galaxy in the universe, though their faintness makes them difficult to detect at large distances. These small ellipticals, containing millions to billions of stars rather than trillions, are particularly abundant in galaxy clusters and groups. They may represent the building blocks from which larger galaxies assembled, or they might be the remnants of larger galaxies that have been stripped of their outer stars through gravitational interactions. The gas content of elliptical galaxies presents an interesting puzzle. While they contain very little cold gas capable of forming stars, many ellipticals are surrounded by vast halos of hot gas, heated to millions of degrees and visible only in X-rays. This hot gas should be cooling and falling toward the galaxy center, potentially fueling new star formation. But in most cases, something prevents this cooling, maintaining the gas at high temperatures for billions of years. The solution to this cooling flow problem appears to involve feedback from the central, supermassive black hole. Even though the black hole might be relatively quiet, accreting only small amounts of material, it can release enough energy through jets and outflows to heat the surrounding gas. This creates a feedback loop, where cooling gas falls toward the center, feeds the black hole, which then releases energy that heats the gas and stops the cooling. This delicate balance can persist for billions of years, preventing new star formation and maintaining the galaxy's red and dead appearance. Some elliptical galaxies show surprising signs of recent activity. These include ellipticals with dust lanes, unusual gas distributions, or evidence of recent star formation. Many of these peculiar ellipticals show signs of recent mergers or interactions, supporting the idea that at least some ellipticals formed relatively recently through the collision of spiral galaxies. The presence of kinematically distinct cores, regions where stars rotate in a different direction from the rest of the galaxy, provides additional evidence for a merger origin. The stellar populations in elliptical galaxies, while predominantly old, show interesting variations. Massive ellipticals typically have higher metallicities than less massive ones, a relationship known as the mass-metallicity relation. This suggests that massive ellipticals were more efficient at retaining the heavy elements produced by their stars, while less massive galaxies lost more of their metals through galactic winds. There are also gradients within individual galaxies, with central regions typically more metal-rich than outer regions. Recent observations have revealed that many elliptical galaxies rotate more than previously thought. While they don't show the organized rotation of spiral galaxies, many ellipticals, particularly lower mass ones, show significant rotation. This has led to a revised classification scheme that divides ellipticals into slow rotators and fast rotators. Fast rotators, which make up the majority of elliptical galaxies, show clear rotation patterns and are often somewhat flattened. Slow rotators, typically the most massive ellipticals, show little rotation and more complex kinematic structures. The environments of elliptical galaxies play crucial roles in their evolution. Ellipticals are much more common in dense environments like galaxy clusters than in isolated regions of space. This environmental dependence, known as the morphology-density relation, likely reflects both the formation mechanisms of ellipticals and the effects of environment on galaxy evolution. In dense environments, galaxies are more likely to merge, have their gas stripped, and experience other interactions that can transform spirals into ellipticals. The future evolution of elliptical galaxies will be slow and gradual. Without significant gas reserves, they cannot form new stars to replace those that die. Over trillions of years, their stellar populations will slowly fade as lower and lower mass stars exhaust their fuel. The galaxies will become progressively fainter and redder, eventually becoming invisible collections of stellar remnants, white dwarfs, neutron stars, and black holes. However, this quiet fade into darkness might be interrupted by future mergers. Even elliptical galaxies will continue to interact and merge with their neighbours over cosmic time. Our own local group, for instance, will eventually see the merger of the Milky Way and Andromeda, likely producing an elliptical galaxy. This new elliptical will later merge with other local group members, ultimately creating a single giant elliptical containing all the stars from dozens of smaller galaxies. The study of elliptical galaxies has revealed fundamental truths about how galaxies form and evolve. They represent one endpoint of galaxy evolution, massive systems that have converted most of their gas into stars and settled into relatively quiet retirement. Yet they continue to grow through mergers and interactions, and their central black holes continue to influence their surroundings through feedback processes that we're only beginning to understand. Beyond the grand spirals and stately ellipticals lies a chaotic realm of irregular galaxies, those cosmic rebels that refuse to conform to neat classifications. These galaxies, lacking the symmetrical beauty of spirals or the smooth regularity of ellipticals, might seem like the outcasts of the galactic family, but they play crucial roles in our understanding of galaxy evolution and the dynamic processes that shape the universe. Irregular galaxies come in many forms, from small amorphous clouds of stars and gas to massive systems distorted by gravitational interactions. The Large and Small Magellanic Clouds, our Milky Way's most prominent satellite galaxies, are perhaps the most famous examples of irregulars. Visible from the southern hemisphere as hazy patches in the night sky, these galaxies have been known to humanity for millennia, though their true nature as separate star systems wasn't understood until the 20th century. The Large Magellanic Cloud, despite being classified as irregular, shows hints of structure that suggest it might once have been a barred spiral galaxy. At about 14,000 light-years across, it's roughly 1/7 the diameter of the Milky Way, but contains enough material to form about 10 billion stars. Its irregular appearance likely results from gravitational interactions with both the Milky Way and its companion, the Small Magellanic Cloud. These interactions have pulled streams of gas from both Magellanic Clouds, creating a vast river of hydrogen gas called the Magellanic Stream that extends across more than half the sky as seen from Earth. This stream, invisible to the naked eye but clearly visible in radio wavelengths, traces the orbital path of the clouds around the Milky Way and provides direct evidence of the ongoing gravitational dance between these galaxies. The Small Magellanic Cloud, more genuinely irregular in structure, presents its own mysteries. Recent observations suggest it might actually be two galaxies aligned along our line of sight, slowly being torn apart by their interactions with the large cloud and the Milky Way. This cosmic dismemberment is happening in slow motion, playing out over hundreds of millions of years, but it demonstrates the violent processes that can transform and destroy irregular galaxies. Irregular galaxies are often sites of intense star formation. Without the density waves of spiral arms or the quenched environments of ellipticals, star formation in irregulars can occur in seemingly random bursts across the galaxy. The Large Magellanic Cloud contains the Tarantula Nebula, one of the most spectacular star-forming regions known, where hundreds of massive stars have recently formed in a starburst that illuminates gas clouds across hundreds of light years. This vigorous star formation in irregular galaxies makes them important contributors to the cosmic census of star formation, especially in the early universe. When we look at distant early galaxies, many appear irregular, suggesting that irregular galaxies might have been more common when the universe was younger. These early irregulars might have been the building blocks that merged to form the larger, more organized galaxies we see today. The chemical composition of irregular galaxies often differs from that of spirals and ellipticals. Many irregulars are metal poor, meaning they have lower concentrations of elements heavier than hydrogen and helium. This metal poverty might indicate that irregulars have been less efficient at retaining the heavy elements produced by their stars, perhaps losing them through galactic winds driven by supernova and stellar winds. Alternatively, some irregulars might be genuinely young systems that haven't had time to build up high metallicities through multiple generations of stars. Studying irregular galaxies provides unique insights into the physics of star formation. Without the complications of spiral density waves or the deep gravitational potentials of massive ellipticals, irregulars offer relatively simple laboratories for understanding how gas converts into stars. The relationship between gas density and star formation rate, known as the Kennicutt-Schmidt law, was first established using observations of irregular galaxies and remains fundamental to our understanding of star formation on galactic scales. The category of irregular galaxies also includes some of the most dramatic objects in the cosmos, galaxies caught in the act of collision and merger. When two galaxies collide, the results can be spectacular and bizarre. The antennae galaxies mentioned earlier show two spirals in the process of merging, their distorted shapes and long tidal tails placing them temporarily in the irregular category. The Cartwheel Galaxy displays a remarkable ring structure created when a smaller galaxy punched through its disk, sending out ripples of star formation like drops in a cosmic pond. These colliding systems provide natural experiments in galaxy evolution. By observing mergers at different stages, astronomers can piece together the sequence of events, from first approach through final coalescence. Computer simulations have become sophisticated enough to reproduce many features of observed merging galaxies, allowing astronomers to determine the masses, orientations, and velocities of the colliding galaxies and predict their future evolution. The process of galaxy collision and merger is far more complex than might be imagined. As galaxies approach each other, their mutual gravity begins to distort their shapes long before they actually touch. Stars in each galaxy feel the gravitational pull of both systems, leading to chaotic orbits that can fling stars far from their original galaxies. These tidal forces can pull out long streams of stars and gas, creating the spectacular tails and bridges seen in many merging systems. When gas clouds from the two galaxies collide, unlike stars which pass by each other, the gas can shock and compress, triggering intense bursts of star formation. These merger-induced starbursts can increase a galaxy's star formation rate by factors of hundreds, creating stars so rapidly that all available gas might be consumed in just a few tens of millions of years. The infrared luminosity from these starbursts can make merging galaxies some of the most luminous objects in the universe. The fate of the supermassive black holes in merging galaxies adds another layer of drama to these cosmic collisions. As galaxies merge, their central black holes spiral toward each other, eventually forming a binary black hole system. These binary black holes continue to orbit each other, gradually losing energy through gravitational interactions with surrounding stars and, in the final stages, through the emission of gravitational waves. The eventual merger of supermassive black holes releases tremendous amounts of energy in gravitational waves, ripples in space-time that we're just beginning to detect with instruments like LIGO and Virgo. Not all galaxy interactions result in mergers. High-speed encounters, particularly common in galaxy clusters, can distort galaxies without leading to coalescence. These harassment interactions can strip gas from galaxies, trigger star formation, and restructure galaxies without actually merging them. Over time, repeated harassment can transform spiral galaxies into irregulars or even ellipticals, contributing to the morphology-density relation observed in galaxy clusters. Ram pressure stripping represents another violent process that can create irregular galaxies. When a galaxy moves through the hot gas that fills galaxy clusters, it experiences a wind that can strip away its own gas. This process can be remarkably efficient, completely removing a galaxy's gas in just a few 100 million years. Galaxies experiencing Ram pressure stripping often show spectacular tails of gas and newly formed stars streaming behind them like cosmic jellyfish. Irregular galaxies also include the mysterious blue compact dwarf galaxies, small systems experiencing intense bursts of star formation that make them appear blue and compact in optical images. These galaxies might represent a phase in the evolution of dwarf galaxies, perhaps triggered by the infall of fresh gas or interactions with neighbouring galaxies. Understanding what triggers and sustains these starbursts remains an active area of research. The role of dark matter in irregular galaxies presents interesting puzzles. Some irregular galaxies appear to be dominated by dark matter to an even greater extent than spirals or ellipticals. The rotation curves of irregular galaxies often rise steadily to their outer edges, indicating large amounts of dark matter. This dark matter dominance might help explain why some irregulars have survived disruption despite their chaotic appearances and relatively shallow gravitational potentials. Irregular galaxies serve as important probes of galaxy formation in different environments. While massive ellipticals dominate dense cluster cores and spirals are common in moderate density environments, irregulars can be found everywhere, from isolated regions to cluster outskirts. This environmental flexibility suggests that irregular morphology can arise through multiple pathways, from isolated evolution in low-mass systems to transformation through interactions in denser environments. The future evolution of irregular galaxies depends strongly on their environment and mass. Isolated irregulars might continue forming stars at modest rates for billions of years, gradually consuming their gas and evolving toward more regular morphologies. Those in groups or clusters face more dramatic fates, likely to be transformed through interactions, stripped of their gas, or absorbed by larger galaxies. Some irregular galaxies might represent transition objects, galaxies caught in the process of transformation from one type to another. A spiral galaxy beginning to merge with another might spend millions of years as an irregular before settling into an elliptical configuration. A small galaxy being stripped of its gas might appear irregular during the stripping process before becoming a dwarf elliptical or ultra-diffuse galaxy. The study of irregular galaxies has revealed the importance of stochastic processes in galaxy evolution. While spirals and ellipticals follow relatively predictable evolutionary paths, irregulars remind us that galaxy evolution can be messy, unpredictable, and highly dependent on local conditions and chance encounters. This stochasticity becomes increasingly important for lower mass galaxies, which are more easily disrupted by interactions and environmental effects. In the vast hierarchy of cosmic structures, dwarf galaxies occupy a humble but fundamentally important position. These small galaxies, containing anywhere from a few million to a few billion stars, are the most numerous type of galaxy in the universe. For every giant galaxy, like the Milky Way or Andromeda, there are dozens of dwarf galaxies, making them the universe's most common galactic citizens. Yet their faintness has long hidden them from our view, and only recently have we begun to appreciate their crucial role in cosmic evolution. Dwarf galaxies come in several varieties, mirroring the classifications of their larger cousins, but with important differences. Dwarf elliptical galaxies are smooth, round, or elongated systems with little gas or ongoing star formation. Dwarf spiral galaxies, though rare, show miniature versions of spiral structure. Dwarf irregular galaxies, perhaps the most common type, are chaotic systems, often rich in gas and actively forming stars. There are also ultra-faint dwarf galaxies discovered only in the past 2 decades, which push the boundaries of what we consider a galaxy. The distinction between the smallest dwarf galaxies and the largest star clusters becomes blurry at the faint end of the galaxy population. Both can contain similar numbers of stars, but galaxies are embedded in dark matter halos, while star clusters are not. This dark matter content represents a fundamental difference, affecting everything from the system structure to its ability to form stars and survive in different environments. Our own local group provides an excellent laboratory for studying dwarf galaxies. The Milky Way has at least 60 known dwarf galaxy satellites, with new ones still being discovered. These range from the relatively massive large and small Magellanic Clouds to ultra-faint dwarfs like Segway 1, which contains only a few hundred stars but sits within a dark matter halo hundreds of times more massive than its stellar content. The discovery of ultra-faint dwarf galaxies has revolutionized our understanding of galaxy formation. These ghostly systems, some containing fewer stars than a modest star cluster, challenge our ideas about the minimum requirements for galaxy formation. They appear to be the survivors of a much larger population of small galaxies that formed in the early universe, most of which were destroyed or absorbed by larger galaxies over cosmic time. The properties of dwarf galaxies provide crucial tests of cosmological models. According to our current understanding of structure formation, small dark matter halos formed first in the early universe, later merging to build larger structures. Dwarf galaxies should therefore be the oldest galactic systems, and indeed, many dwarf galaxies contain ancient stellar populations dating back 12 billion years or more. But there's a problem known as the missing satellites problem. Simulations of structure formation predict that galaxies like the Milky Way should have hundreds or thousands of dark matter subhalos massive enough to host dwarf galaxies. Yet we observe far fewer dwarf galaxies than predicted. This discrepancy might indicate that galaxy formation becomes inefficient below a certain mass threshold, or it might point to physics beyond our standard cosmological model. The star formation histories of dwarf galaxies reveal diverse evolutionary pathways. Some dwarf galaxies formed all their stars in a single burst early in cosmic history, then shut down star formation completely. Others have formed stars continuously at low rates for billions of years. Still others show episodic star formation, with periods of activity separated by long quiescent phases. Understanding what drives these different histories remains a major challenge in galaxy evolution studies. The role of feedback in dwarf galaxies is particularly important due to their shallow gravitational potential wells. When massive stars explode as supernovae in a dwarf galaxy, the energy released can be comparable to the gravitational binding energy of the galaxy's gas. This means that a burst of star formation can literally blow all the gas out of a dwarf galaxy, shutting down further star formation. This feedback process might explain why many dwarf galaxies have such low star formation efficiencies and why some have no gas at all. Dwarf galaxies also serve as important probes of reionization. the epoch when the first stars and galaxies ionized the neutral hydrogen that filled the early universe. The smallest dwarf galaxies we see today might be fossils from this era. Their star formation shut down when rionization heated and ionized the intergalactic gas, preventing further gas accretion onto small halos. The properties of these ancient dwarfs therefore provide clues about conditions in the early universe. The chemical evolution of dwarf galaxies differs markedly from that of larger galaxies. Many dwarf galaxies show very low metallicities, indicating inefficient retention of the heavy elements produced by their stars. Some ultrafaint dwarfs contain stars with such low metallicities that they must have formed from gas enriched by only one or two previous supernovae. These extremely metal-poor stars provide windows into the properties of the first stellar generations. Tidal interactions play major roles in the evolution of dwarf galaxies, especially those orbiting larger galaxies. As dwarf galaxies orbit their massive hosts, tidal forces can strip away their outer stars, creating stellar streams that trace their orbital paths. The Sagittarius dwarf galaxy, currently being torn apart by the Milky Way, has created streams of stars that wrap around our galaxy multiple times. These streams provide archaeological evidence of past interactions and help us understand how large galaxies grow by consuming smaller ones. The transformation of dwarf galaxies through environmental processes is particularly dramatic. A gas-rich dwarf irregular galaxy falling into a galaxy cluster can be completely transformed, its gas stripped away and star formation halted, leaving behind a gas-poor dwarf elliptical. This transformation can happen remarkably quickly, in just a few 100 million years, fundamentally changing the galaxy's properties and future evolution. Some dwarf galaxies show evidence of surprisingly massive black holes at their centers. While not all dwarf galaxies contain central black holes, those that do challenge our understanding of black hole formation and growth. These intermediate mass black holes, ranging from thousands to millions of solar masses, might be remnants of the seed black holes that grew into the supermassive black holes we see in larger galaxies. The dark matter content of dwarf galaxies makes them important laboratories for studying the nature of dark matter itself. The density profiles of dark matter halos in dwarf galaxies can test different dark matter models. Cold dark matter predicts centrally concentrated halos with steep density profiles, while some observations suggest shallower, more cooled profiles. This cusp core problem remains one of the challenges to our standard cosmological model. Recent discoveries have revealed populations of ultra-diffuse galaxies, dwarf galaxies with sizes comparable to the Milky Way, but only 1% of its stellar mass. These ghostly galaxies are so diffuse that you can see right through them. How they formed and why they didn't collapse to form more concentrated systems remains mysterious. Some might be failed galaxies that lost their gas before they could form many stars, while others might have been puffed up by intense feedback or tidal interactions. The connection between dwarf galaxies and globular clusters provides insights into both types of systems. Some dwarf galaxies contain no globular clusters, while others have surprisingly rich globular cluster systems for their size. The most massive globular clusters might actually be the stripped nuclei of dwarf galaxies that were otherwise destroyed by tidal interactions. This connection blurs the distinction between star clusters and galaxies at low masses. Dwarf galaxies in different environments show markedly different properties. Field dwarfs, isolated in space, tend to be gas-rich and actively forming stars. Those in groups and clusters are more likely to be gas-poor and quiescent. This environmental dependence extends to their structural properties, with cluster dwarfs showing signs of tidal disturbance and harassment that are absent in isolated systems. The contribution of dwarf galaxies to cosmic star formation and chemical enrichment, while modest on a per-galaxy basis, becomes significant when their vast numbers are considered. In the early universe, dwarf galaxies might have been responsible for a large fraction of all star formation. The metals they produced and expelled through galactic winds enriched the intergalactic medium, providing the raw materials for subsequent generations of galaxies. Looking to the future, dwarf galaxies will continue to evolve through interactions and environmental processes. Those orbiting larger galaxies will eventually be absorbed, their stars joining the halos of their host galaxies. Isolated dwarfs might continue forming stars at low rates for trillions of years, outlasting their more massive cousins. The ultimate fate of dwarf galaxies depends on the fate of the universe itself and the nature of dark energy. When we zoom out from individual galaxies to observe the universe on its largest scales, we discover that galaxies are not randomly scattered through space, but organized into a magnificent cosmic web of clusters, superclusters, filaments, and voids. Galaxy clusters represent the largest gravitationally bound structures in the universe, massive congregations containing hundreds to thousands of galaxies, vast reservoirs of hot gas, and enormous amounts of dark matter, all held together in a complex gravitational dance that has been choreographed over billions of years. The discovery of galaxy clusters dates back to the 18th century, when Charles Messier and William Herschel noted concentrations of nebulae in certain regions of the sky. But it wasn't until the 20th century that astronomers recognized these nebulae as galaxies and understood that clusters represent genuine physical associations of galaxies bound by gravity. The Virgo cluster, the nearest large cluster to Earth at about 54 million light-years away, contains over 1,300 known galaxies and dominates our local cosmic neighbourhood. Galaxy clusters range enormously in size and mass. Small groups like our own local group contain just a few dozen galaxies, while massive clusters can host thousands of galaxies within a region just a few million light-years across. The Coma cluster, one of the nearest massive clusters, contains over 1,000 galaxies brighter than magnitude 19, with hundreds more fainter systems. The total mass of such clusters can exceed 1 quadrillion solar masses, making them the most massive collapsed structures in the universe. But galaxies themselves represent only a small fraction of a cluster's total mass. When astronomers first measured the velocities of galaxies within clusters in the 1930s, they discovered that galaxies were moving far too fast to be held together by their mutual gravitational attraction alone. This was one of the first indications of dark matter's existence. Modern measurements confirm that galaxies account for only about 1% of a cluster's mass, with dark matter making up about 85% and hot gas contributing the remaining 14%. The hot gas that fills galaxy clusters, called the intracluster medium, is one of their most remarkable features. Heated to temperatures of tens of millions of degrees, this gas glows brightly in X-rays, making galaxy clusters some of the most luminous X-ray sources in the sky. The gas has been heated by the enormous gravitational energy released as the cluster assembled, with infalling material accelerated to thousands of kilometers per second before being shock heated as it encounters the existing cluster gas. This hot gas plays crucial roles in cluster evolution. Its pressure can strip gas from infalling galaxies through ram pressure stripping, transforming gas-rich spirals into gas-poor ellipticals and lenticulars. The gas also provides a medium through which energy from active galactic nuclei can propagate, with jets from supermassive black holes inflating bubbles and driving waves through the intracluster medium. These feedback processes help regulate star formation in cluster galaxies and prevent the hot gas from cooling catastrophically. The formation of galaxy clusters is a spectacular process that continues today. Clusters form at the intersections of cosmic filaments, where dark matter and gas flow together under gravity's influence. As smaller groups and individual galaxies fall into growing clusters, they can reach velocities of thousands of kilometers per second. When groups merge with clusters, or clusters collide with each other, the kinetic energy released can exceed the total energy output of all the stars in the cluster over their entire lifetimes. The bullet cluster provides a dramatic example of cluster collision caught in the act. In this system, a smaller cluster has passed through a larger one at about 4,000 kilometers per second. The collision has separated different components of the clusters, with the hot gas lagging behind the galaxies and dark matter due to ram pressure. This separation provides some of the strongest evidence for dark matter's existence, as the gravitational lensing shows that most of the mass is associated with the dark matter rather than the visible gas. Galaxy clusters act as gravitational lenses, bending light from more distant objects. This gravitational lensing can magnify distant galaxies, allowing us to see objects that would otherwise be too faint to detect. Strong lensing near cluster cores can produce multiple images of the same background galaxy or stretch galaxies into long arcs. Weak lensing in cluster outskirts causes subtle distortions that, when measured statistically, reveal the distribution of dark matter throughout the cluster. The galaxy population in clusters differs markedly from that in less dense environments. While spiral galaxies dominate the field population, elliptical and lenticular galaxies predominate in cluster cores. This morphology-density relation reflects the various processes that transform galaxies in dense environments. Mergers, harassment, ram pressure stripping, and strangulation all contribute to morphological transformation, converting blue, star-forming spirals into red, quiescent early-type galaxies. At the centers of many clusters sit enormous elliptical galaxies, known as brightest cluster galaxies, or BCGs. These cosmic giants can contain several trillion stars and extend for hundreds of thousands of light years. They grow through a special form of galactic cannibalism, sitting at the bottom of the cluster's potential well, where they can capture and merge with other galaxies that sink toward the center through dynamical friction. Some BCGs show multiple nuclei, evidence of recent meals not yet fully digested. The evolution of galaxies within clusters follows predictable patterns. As galaxies fall into clusters, for the first time, they often experience enhanced star formation triggered by compression of their gas. This phase is brief, however, as environmental processes quickly remove the gas needed for continued star formation. Ram pressure stripping can completely remove a galaxy's gas in just a few 100 million years, while strangulation, the cut-off of fresh gas supply, causes a slower decline in star formation over billions of years. Clusters also host unique galaxy populations not found elsewhere. Jellyfish galaxies show spectacular tails of gas and young stars stripped by ram pressure as they plunge through the intracluster medium. These galaxies provide natural laboratories for studying star formation under extreme conditions, as stars continue to form in the stripped gas tails even after being removed from their parent galaxies. Some of these orphaned star-forming regions might become isolated star clusters or even small galaxies in their own right. The dynamics of galaxy clusters are complex and fascinating. Galaxies orbit within clusters at typical velocities of 500 to 1500 kilometers per second, far exceeding the escape velocity from individual galaxies. These high velocities mean that galaxy collisions in clusters rarely result in mergers. Instead, galaxies experience high-speed encounters that can distort their shapes, trigger star formation, and strip away loosely bound material without actually merging. Clusters themselves are not isolated but connected to the larger cosmic web through filaments of galaxies and dark matter. These filaments channel galaxies and gas into clusters, feeding their growth. Where multiple filaments intersect, superclusters form, vast associations of clusters and groups extending across hundreds of millions of light-years. The Laniakea supercluster, our home supercluster, contains about 100,000 galaxies spread across a region 500 million light-years in diameter. Superclusters represent the largest coherent structures in the universe, but they are not gravitationally bound. The accelerating expansion of the universe, driven by dark energy, prevents superclusters from collapsing under their own gravity. Instead, they are transient features in the cosmic web, associations that will disperse as cosmic expansion accelerates. The Great Attractor, a gravitational anomaly in the direction of the Centaurus and Norma clusters, influences the motion of galaxies across our entire supercluster, causing a large-scale flow of galaxies toward this region. The cosmic web itself, revealed through large galaxy surveys, shows a remarkable structure of filaments, walls, and voids. Filaments of galaxies stretch between clusters like cosmic highways, while vast voids, regions nearly empty of galaxies, occupy most of the universe's volume. This structure arose from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years into the large-scale structure we observe today. Observations of clusters at different distances, and therefore different cosmic epochs, reveal how these structures have evolved over time. Distant clusters tend to be less massive and more actively forming stars than nearby clusters, showing that clusters have grown and evolved significantly over cosmic time. The rate of cluster formation peaked when the universe was about half its current age and has been declining since then as cosmic acceleration makes it harder for new clusters to collapse. The future evolution of galaxy clusters will be shaped by dark energy and the accelerating expansion of the universe. Clusters that are already gravitationally bound will remain so, slowly growing as they absorb remaining infalling material. But no new large clusters will form, and existing clusters will become increasingly isolated from each other. Over trillions of years, clusters will become island universes, isolated and alone in an ever-expanding cosmos. Throughout our journey exploring galaxies, we've repeatedly encountered an invisible presence that shapes everything we observe: dark matter. This mysterious substance, which neither emits nor absorbs light, makes up approximately 85% of all matter in the universe. Its gravitational influence is written across the cosmos, from the rotation of individual galaxies to the larger structures in the universe. Understanding dark matter is perhaps the greatest challenge in modern astronomy, a puzzle whose solution would revolutionize our understanding of physics and cosmology. The story of dark matter's discovery is a testament to careful observation and scientific reasoning. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster and noticed that galaxies were moving far too fast to be held together by the gravity of visible matter alone. He coined the term Dunkelmaterie, or dark matter, to describe the missing mass. Around the same time, Dutch astronomer Jan Oort found discrepancies in the motions of stars in the solar neighbourhood that suggested more matter than could be seen. But it was the work of Vera Rubin and Kent Ford in the 1970s that truly established dark matter as a fundamental component of galaxies. They measured the rotation speeds of stars and gas in spiral galaxies at different distances from the galactic centres. According to Newton's laws and the visible distribution of matter, stars in the outer regions of galaxies should orbit more slowly than those near the centre, just as outer planets in our solar system orbit more slowly than inner planets. Instead, they found that orbital speeds remained roughly constant or even increased with distance, the flat rotation curves that have become a hallmark of dark matter's presence. These observations implied that galaxies are embedded in vast halos of invisible matter extending far beyond the visible stars. The amount of dark matter needed to explain the observations dwarfs the normal matter content. In a typical spiral galaxy like the Milky Way, the dark matter halo extends to at least 10 times the radius of the visible disk and contains 5 to 10 times more mass than all the stars, gas, and dust combined. The distribution of dark matter in galaxies has been mapped through various techniques. Gravitational lensing allows astronomers to map dark matter in distant galaxies and clusters by measuring how their gravity bends light from background objects. The motion of satellite galaxies and stellar streams reveals the shape and extent of dark matter halos around large galaxies. Computer simulations that start from the tiny fluctuations observed in the cosmic microwave background successfully reproduce the large-scale structure of the universe only when dark matter is included. These studies reveal that dark matter halos are not uniform spheres, but have complex structures. They are typically triaxial, somewhat football-shaped rather than perfectly round. The density of dark matter increases toward the center of halos, though the exact shape of this density profile in the innermost regions remains controversial. Simulations predict steep central cusps, while some observations suggest flatter cores, a discrepancy known as the cusp core problem. Dark matter halos also contain substructure, smaller clumps of dark matter orbiting within the main halo. These subhalos can host dwarf galaxies, though many appear to be completely dark, containing no stars at all. The abundance and distribution of subhalos provide important tests of dark matter models and help us understand how galaxies form within dark matter halos. The nature of dark matter remains one of the great mysteries in physics. We know what dark matter is not. It's not normal atoms, not black holes in sufficient numbers, not neutrinos, but determining what it is has proven extraordinarily difficult. The leading candidates are weakly interacting massive particles, or WIMPs, hypothetical particles that interact only through gravity and possibly the weak nuclear force. Despite decades of searches using underground detectors, particle accelerators, and astronomical observations, no direct detection of dark matter particles has been confirmed. Alternative theories of dark matter continue to be explored. Axions, extremely light particles originally proposed to solve a problem in quantum chromodynamics, could constitute dark matter if they exist in sufficient numbers. Primordial black holes, formed in the early universe rather than from dying stars, have been proposed, though observations have ruled out most mass ranges for such objects. Some scientists even propose modifications to our theory of gravity rather than new particles, though these modified gravity theories struggle to explain all the observations that dark matter handles naturally. The role of dark matter in galaxy formation is fundamental. In the early universe, dark matter began clustering under its own gravity, while normal matter was still coupled to radiation. This head start allowed dark matter to form the gravitational wells into which normal matter would later fall. Without dark matter, galaxies couldn't have formed as quickly as they did. The universe would look very different, perhaps with no galaxies at all or only much smaller structures than we observe. Dark matter halos grow hierarchically through mergers and accretion. Small halos form first and merge to create progressively larger structures. This bottom-up assembly continues today, with galaxies embedded in their dark matter halos merging to form larger galaxies. The merger history of dark matter halos is preserved in their structure, with surviving subhalos and stellar streams recording past accretion events. The connection between dark matter halos and the galaxies they host is complex and still not fully understood. Not all dark matter halos contain galaxies. Below a certain mass threshold, halos appear to be dark. The efficiency of galaxy formation peaks at a particular halo mass, roughly 1 trillion solar masses, corresponding to galaxies like the Milky Way. More massive halos host proportionally less stellar mass, possibly due to feedback from active galactic nuclei, while less massive halos also have lower star formation efficiency, perhaps due to supernova feedback and rionization. Dark matter influences galaxy evolution in numerous ways beyond providing gravitational potential wells. The depth of a dark matter halo determines how much gas a galaxy can retain against feedback processes. The angular momentum of dark matter halos influences the rotation and morphology of the galaxies that form within them. Interactions between dark matter subhalos and galactic disks can trigger spiral arms, bars, and warps. The distribution of dark matter on the largest scales forms the cosmic web that defines the universe's structure. Dark matter filaments channel galaxies toward clusters, while dark matter voids remain largely empty. This cosmic web arose from tiny quantum fluctuations in the early universe, with dark matter's gravity amplifying these seeds into the structures we observe today. The pattern of the cosmic web provides a fossil record of these primordial fluctuations and the universe's subsequent evolution. Gravitational lensing by dark matter has become a powerful tool for cosmology. Weak lensing surveys measure subtle distortions in the shapes of millions of galaxies to map the dark matter distribution across large areas of sky. These maps reveal the cosmic web in unprecedented detail and provide independent measures of cosmological parameters. Strong lensing by galaxy clusters allows us to map dark matter in these systems with high precision, sometimes revealing discrepancies with the distribution of visible matter that provide evidence for dark matter's existence. The future of dark matter research holds great promise. New experiments continue to push the boundaries of sensitivity in searching for dark matter particles. Larger galaxy surveys will map the dark matter distribution across most of the observable universe. Advanced simulations incorporating both dark matter and normal matter physics will provide better predictions for comparison with observations. The detection and study of gravitational waves might reveal dark matter through its influence on merging black holes or through exotic compact objects. Understanding dark matter is crucial for predicting the future evolution of galaxies and the universe. Dark matter halos will continue to grow through accretion and mergers, though at a decreasing rate due to cosmic acceleration. The ultimate fate of dark matter depends on its nature. If dark matter particles are stable, they will outlive all stars and normal matter. If they can decay or annihilate, albeit very slowly, dark matter might eventually disappear, leaving only its gravitational legacy in the structure of the universe. At the hearts of some galaxies lurk monsters of almost incomprehensible power, supermassive black holes actively devouring matter and releasing energy that can outshine entire galaxies. These active galactic nuclei, or AGN, represent some of the most extreme phenomena in the universe. When particularly luminous, they're called quasars, quasi-stellar radio sources that puzzled astronomers for years after their discovery. These cosmic lighthouses can be seen across billions of light years, their brilliance powered by matter spiraling into black holes millions or billions of times more massive than our Sun. The discovery of quasars in the early 1960s revolutionized our understanding of the universe. Radio astronomers had detected point-like radio sources that, when examined optically, appeared as faint blue stars, but their spectra showed emission lines that couldn't be identified with any known elements. The breakthrough came when astronomer Martin Schmidt realized these were ordinary spectral lines massively redshifted, indicating the objects were billions of light years away. For these objects to be visible at such distances, they had to be incredibly luminous, hundreds of times brighter than entire galaxies, yet varying in brightness over periods of just days or weeks, indicating the energy source was no larger than our solar system. The physics of active galactic nuclei centers on accretion, the process of matter falling into the supermassive black hole. As gas, dust, and even disrupted stars spiral inward, they form an accretion disk, a swirling maelstrom of matter heated to millions of degrees by friction and gravitational compression. The inner edge of this disk, just outside the black hole's event horizon, represents one of the most extreme environments in the universe, where matter reaches speeds approaching that of light and temperatures that dwarf those in stellar cores. The efficiency of this process is remarkable. Through accretion onto a black hole, matter can convert up to 40% of its rest mass into energy, compared to less than 1% for nuclear fusion in stars. This extraordinary efficiency explains how quasars can be so luminous. A quasar converting matter to energy at a rate of just 10 solar masses per year can outshine 1 trillion stars. Some of the most powerful quasars consume hundreds of solar masses annually, generating luminosities that boggle the mind. But not all the matter falling toward a black hole is consumed. Some is ejected in powerful jets that shoot from the poles of the black hole at speeds exceeding 99% of the speed of light. These jets, confined and accelerated by twisted magnetic fields, can extend for millions of light years, far beyond the host galaxy. When we observe these jets from different angles, we see different types of AGN, from blazars where we're looking straight down the jet, to radio galaxies where we see the jets from the side. The variety of active galactic nuclei forms what astronomers call the AGN zoo. Seifert galaxies, named after Carl Seifert, who first described them in the 1940s, are spiral galaxies with bright nuclei that show broad emission lines indicating gas moving at thousands of kilometers per second. Radio galaxies, often giant ellipticals, produce powerful jets that create enormous radio-emitting lobes as they plough into intergalactic space. Blazars show rapid, dramatic variability as their jets point almost directly at Earth. Each type provides a different viewing angle of the same basic phenomenon, a supermassive black hole actively feeding. The unification model of AGN suggests that all these different types are fundamentally the same phenomenon viewed from different orientations. Surrounding the accretion disk is a thick torus of dust and gas. When we view the system edge-on, this torus blocks our direct view of the accretion disk and broadline region, and we see a Type 2 or obscured AGN. When viewed face-on, we can see directly into the central engine, observing a Type 1 or unobscured AGN. This elegant model explains much of the diversity we observe, though the full picture is undoubtedly more complex. The relationship between supermassive black holes and their host galaxies is intimate and profound. There's a remarkably tight correlation between the mass of a galaxy's central black hole and the velocity dispersion of stars in the galaxy's bulge, the M-sigma relation. This correlation holds across a wide range of galaxy types and masses, suggesting that galaxies and their central black holes grow together in a coordinated dance. But how this coordination is maintained remains one of the key questions in galaxy evolution. Feedback from AGN plays a crucial role in galaxy evolution. The energy released by an active nucleus can heat and expel gas from the host galaxy, shutting down star formation. In galaxy clusters, AGN jets inflate bubbles in the hot intracluster medium, preventing it from cooling and forming stars. This AGN feedback might solve several long-standing problems in galaxy formation, explaining why massive galaxies have relatively few stars for their dark matter halo masses, and why galaxy clusters don't experience cooling catastrophes. The duty cycle of AGN activity reveals that most supermassive black holes spend most of their time in a quiescent state. Our own Milky Way's central black hole, Sagittarius A star, is currently very quiet, accreting at less than 1/10,000,000th of a solar mass per year. But evidence suggests it was more active in the past. Fermi bubbles, enormous structures of hot gas extending above and below the galactic center, might be remnants of an AGN outburst a few million years ago. Most galaxies probably experience periodic episodes of AGN activity triggered by fresh supplies of fuel. What triggers AGN activity is a crucial question. Major galaxy mergers can funnel gas toward the central black hole, triggering intense activity. But many AGN occur in galaxies with no signs of recent mergers. Secular processes like bar-driven gas, inflow or disk instabilities might trigger lower-level activity. The stochastic accretion of gas clouds, or even the tidal disruption of unfortunate stars passing too close to the black hole, can cause temporary flare-ups. Quasars were most common when the universe was 2 to 3 billion years old, an era sometimes called cosmic noon. During this period, both star formation and black hole growth peaked. The most distant quasars we observe existed when the universe was less than 1 billion years old, their light having travelled for over 13 billion years to reach us. These ancient quasars pose challenges for our understanding of black hole growth, as they contain black holes of billions of solar masses that somehow formed in the universe's first billion years. The growth of supermassive black holes from smaller seeds is a topic of intense research. Black holes might have started as the remnants of the first generation of massive stars, weighing perhaps 100 solar masses. Through accretion and mergers, these could grow to supermassive scales. Alternatively, massive seeds might have formed through the direct collapse of primordial gas clouds, starting with masses of thousands or hundreds of thousands of solar masses. The detection of intermediate mass black holes, weighing thousands to hundreds of thousands of solar masses, provides clues about this growth process. The environments around active galactic nuclei are extreme and complex. The broadline region, clouds of gas moving at thousands of kilometers per second, produces the characteristic broad emission lines in AGN spectra. Further out, the narrow line region contains gas moving more slowly, ionized by radiation from the central engine. The host galaxy itself often shows signs of disturbance, with enhanced star formation or, conversely, suppressed star formation due to AGN feedback. Variability is a defining characteristic of AGN. Quasars can change brightness significantly over timescales from hours to years. This variability provides information about the size and structure of the emitting regions. Reverberation mapping, which measures the time delay between variations in different parts of the spectrum, allows astronomers to map the structure of AGN despite their great distances. These studies reveal the stratified structure of AGN, with different emission lines originating at different distances from the black hole. The most dramatic variability occurs in tidal disruption events, when a star ventures too close to a supermassive black hole and is torn apart by tidal forces. Half the stellar debris escapes, while the other half forms an accretion disk, causing a bright flare that can last months to years. These events provide unique opportunities to study normally quiescent black holes and to witness the formation of accretion disks in real time. The impact of AGN on their surroundings extends far beyond their host galaxies. Quasar winds, flowing outward at speeds of thousands of kilometers per second, can affect gas across the entire galaxy and even into the circumgalactic medium. Radio jets can heat gas in galaxy clusters, affecting the evolution of hundreds of galaxies. The ultraviolet radiation from quasars in the early universe contributed to reionization, the process that ended the cosmic dark ages. Multi-wavelength observations are essential for understanding AGN. Radio observations reveal jets and lobes. Infrared observations penetrate dust to see obscured nuclei. Optical and ultraviolet observations show the accretion disk and emission line regions. X-ray observations probe the innermost regions near the black hole. Gamma-ray observations detect the most energetic processes in jets. Each wavelength provides a different piece of the puzzle, and only by combining them all can we understand these complex systems. The discovery of changing-look AGN has added a new dimension to our understanding. These objects transition between different AGN types over timescales of years to decades, their broad emission lines appearing or disappearing. This phenomenon might be caused by changes in accretion rate or changes in the obscuring material around the nucleus. These transitions challenge simple unification models and suggest that AGN can experience dramatic changes in their properties on human timescales. The role of magnetic fields in AGN is increasingly recognized as crucial. Magnetic fields thread the accretion disk, transporting angular momentum outward and allowing matter to fall inward. They also collimate and accelerate jets, converting rotational energy from the black hole into kinetic energy of outflowing matter. The most powerful jets might extract energy directly from spinning black holes through the Blandford-Znajek mechanism, where magnetic field lines threading the ergosphere are twisted by the black hole's rotation. Supermassive black hole binaries form when galaxies merge, bringing their central black holes together. These binaries spiral inward through dynamical friction and gravitational wave emission. The final merger releases enormous amounts of energy in gravitational waves, potentially kicking the merged black hole out of the galaxy center or even out of the galaxy entirely. Several candidate binary AGN have been identified, showing periodic variability or double-peaked emission lines that might indicate orbital motion. The future of AGN research is bright with new facilities and techniques. The Event Horizon Telescope has already imaged the shadows of black holes in M87 and our own galaxy and will target more AGN. Gravitational wave detectors like LISA will detect merging supermassive black holes across the universe. Time domain surveys will discover AGN variability and tidal disruption events in unprecedented numbers. These observations will reveal how black holes grow, how they interact with their host galaxies, and how they shape the evolution of the universe. The story of how galaxies change and develop over billions of years is written across the sky in light that has travelled for most of the universe's history to reach us. When we observe distant galaxies, we see them not as they are now, but as they were when their light began its journey. This cosmic time machine allows us to witness galaxy evolution directly, observing how galaxies in the early universe differ from those we see nearby, and piecing together the processes that transformed simple gas clouds into the diverse array of galaxies we observe today. In the very early universe, before the first galaxies formed, the cosmos was a much simpler place. The first few 100 million years after the Big Bang saw the gradual assembly of the first proto-galaxies, small clumps of gas and dark matter beginning to collapse under gravity. These early structures were nothing like the grand spirals and massive ellipticals we see today. They were small, irregular, and composed almost entirely of hydrogen and helium, the only elements available in significant quantities at that time. The James Webb Space Telescope has revolutionized our view of these early galaxies, revealing surprises that challenge our theoretical models. Some galaxies appear more massive and more mature than expected at very early times, suggesting that galaxy assembly might have proceeded more rapidly than previously thought. We see galaxies that existed when the universe was only 300 million years old, already containing hundreds of millions of stars and showing signs of complex structure and chemical enrichment. The first billion years of cosmic history saw dramatic evolution in the galaxy population. The earliest galaxies were sites of intense star formation, converting gas into stars at rates that would exhaust their fuel supplies in just a few 100 million years. These starburst galaxies were producing stars hundreds or thousands of times faster than the Milky Way does today. The universe was experiencing its most active period of star formation, with the cosmic star formation rate rising rapidly as more and more galaxies assembled and began processing their gas into stars. During this early epoch, galaxies were also growing through frequent mergers. The universe was smaller and denser then, and galaxies were closer together. Computer simulations suggest that a typical galaxy might have experienced dozens of significant mergers during the first few billion years of cosmic history. These mergers not only increased galaxy masses, but also triggered bursts of star formation and fed the growth of central supermassive black holes. The peak epoch of cosmic star formation occurred when the universe was about 3 to 4 billion years old, a period astronomers call cosmic noon. During this time, the average star formation rate in the universe was about 10 times higher than it is today. Galaxies were consuming their gas reserves rapidly, building up their stellar populations in a cosmic construction boom. Many of the stars we see in galaxies today, including many in our own Milky Way, formed during this remarkable period. But this couldn't last forever. By about 8 billion years ago, the cosmic star formation rate had begun to decline, a trend that continues to the present day. This decline, sometimes called cosmic downsizing, reflects several factors. Galaxies were running out of cold gas, the fuel for star formation. Feedback from supernovae and active galactic nuclei was heating and ejecting gas, making it unavailable for star formation. The expansion of the universe was making it harder for galaxies to accrete fresh gas from their surroundings. The concept of the star formation main sequence has become central to understanding galaxy evolution. At any given epoch, star-forming galaxies follow a relatively tight relationship between their stellar mass and star formation rate. Galaxies on this main sequence are forming stars at a steady pace, sustainably processing their gas into stars. Galaxies above the main sequence are experiencing starbursts, often triggered by mergers or other processes. Galaxies below or off the main sequence have had their star formation suppressed or quenched. The process of galaxy quenching, the cessation of star formation, is one of the most important but least understood aspects of galaxy evolution. Observations show that the fraction of quenched galaxies increases with both stellar mass and environmental density. Massive galaxies are more likely to be quenched than low-mass galaxies, and galaxies in clusters are more likely to be quenched than field galaxies. But the physical mechanisms responsible for quenching remain debated. Several quenching mechanisms have been proposed and likely all play roles in different circumstances. Feedback from active galactic nuclei can heat or expel gas from galaxies, particularly massive ones. Environmental processes like ram pressure stripping and strangulation can remove gas from galaxies in dense environments. Morphological quenching might occur when galaxies develop stable bulges that prevent gas from forming stars efficiently. The relative importance of these mechanisms likely depends on galaxy mass, environment, and cosmic epoch. The transformation of galaxy morphologies over cosmic time tells another aspect of the evolutionary story. In the distant universe, irregular and peculiar galaxies were more common than today, reflecting the importance of mergers and interactions. The fraction of disk galaxies has remained relatively constant over much of cosmic history, though the properties of disks have evolved. Early disks were thicker, more turbulent, and more gas-rich than modern spirals. The fraction of elliptical and lenticular galaxies has increased over time, particularly in dense environments. The role of galaxy mergers in driving morphological transformation has been extensively studied through both observations and simulations. Major mergers between galaxies of comparable mass can destroy disk structures and create elliptical galaxies. Minor mergers, where a large galaxy absorbs a much smaller one, can build up bulges and thick disks without completely destroying thin disks. The merger rate was higher in the past when the universe was denser, but mergers continue to play important roles in galaxy evolution today. Secular evolution, slow changes driven by internal processes rather than mergers, has become increasingly important as the merger rate has declined. Bars can funnel gas toward galaxy centers, building up bulges and feeding black holes. Spiral density waves can redistribute angular momentum and cause gas to flow inward. Star formation feedback can drive gas flows that alter galaxy structure. These processes operate over billions of years, gradually transforming galaxies even in the absence of major interactions. The chemical evolution of galaxies provides another window into their histories. As successive generations of stars form and die, they enrich the interstellar medium with heavy elements. The metallicity of a galaxy's stars and gas therefore provides a fossil record of its star formation history. Observations show that galaxy metallicity correlates with stellar mass, the mass-metallicity relation, indicating that more massive galaxies have been more efficient at retaining the metals produced by their stars. The evolution of the mass-metallicity relation over cosmic time reveals how galaxies have been enriched. At any given stellar mass, galaxies in the early universe had lower metallicities than similar mass galaxies today. This evolution reflects ongoing star formation and metal production, but also gas flows. Infalling pristine gas can dilute metallicity, while outflows preferentially remove metals. The balance between these processes shapes the chemical evolution of galaxies. The growth of supermassive black holes is intimately connected to galaxy evolution. The tight correlations between black hole mass and galaxy properties suggest coordinated growth, but the mechanisms maintaining this coordination remain unclear. Observations of distant galaxies suggest that black holes might have grown earlier or faster than their host galaxies, with the stellar populations catching up later. The peak of quasar activity preceded the peak of cosmic star formation slightly, suggesting that black hole growth might regulate subsequent star formation. Environmental effects on galaxy evolution have operated throughout cosmic history, but in different ways at different times. In the early universe, galaxies in overdense regions evolved faster, forming stars earlier and building up stellar mass more quickly. This accelerated evolution in dense environments continues today, with cluster galaxies typically older and more evolved than field galaxies of similar mass. But dense environments also strip gas and suppress star formation, transforming late-type galaxies into early types. The concept of archaeological downsizing adds another layer to our understanding of galaxy evolution. While more massive galaxies assembled later through hierarchical merging, their stellar populations are paradoxically older on average. This indicates that star formation was more efficient in the progenitors of massive galaxies, which formed most of their stars quickly at early times. Less massive galaxies formed their stars more gradually over extended periods, resulting in younger average stellar ages despite earlier assembly times. The role of gas accretion in fueling continued star formation has become increasingly appreciated. Galaxies cannot sustain star formation for billions of years using only their initial gas supply. Fresh gas must be accreted from the intergalactic medium or through minor mergers. Cold mode accretion, where gas flows along dark matter filaments into galaxies, might dominate for lower mass galaxies and at early times. Hot mode accretion, where gas is shock heated before cooling onto galaxies, becomes important for massive galaxies at later times. Feedback processes regulate galaxy evolution in complex ways. Stellar feedback from supernovae and stellar winds can trigger star formation by compressing nearby gas or suppress it by heating and dispersing gas. AGN feedback can quench star formation in massive galaxies but might also trigger star formation in some circumstances. The balance between positive and negative feedback helps determine galaxy properties and might explain the relatively tight scaling relations observed. The diversity of evolutionary pathways is one of the most striking aspects of galaxy evolution. Two galaxies with similar initial conditions can evolve very differently depending on their merger histories, environments, and stochastic processes. This diversity increases toward lower masses, where individual events can have larger relative impacts. Understanding this diversity and the processes that drive it remains a major challenge in galaxy evolution studies. Looking toward the future of galaxy evolution, we can make predictions based on current trends and physical understanding. The cosmic star formation rate will continue to decline as the universe expands and galaxies exhaust their gas supplies. Galaxy mergers will become less common as cosmic expansion accelerates. Environmental effects will continue to transform galaxies in groups and clusters. Over trillions of years, star formation will cease almost entirely, leaving a universe populated by slowly fading stellar systems. As we contemplate the future of galaxies, we're peering into a cosmic destiny that stretches trillions of years into the future. A timeline so vast that the current age of the universe, 13.8 billion years, represents just the opening chapter of a much longer story. The galaxies we see today, in all their magnificent variety, are temporary structures in an evolving cosmos, and their ultimate fates are determined by the fundamental forces and components that govern our universe, particularly dark energy and its accelerating expansion. The next few billion years will see continued evolution of galaxies through processes already underway. Our own Milky Way faces a dramatic transformation as it approaches its collision with the Andromeda Galaxy. Currently separated by 2.5 million light-years, these two spiral giants are approaching each other at about 110 kilometers per second. In approximately 4 billion years, they will begin their gravitational dance, a cosmic ballet that will play out over hundreds of millions of years. Computer simulations of this future collision paint a spectacular picture of transformation. As the galaxies approach, tidal forces will distort their shapes, pulling out long streams of stars and gas. The galaxies will likely pass through each other initially, their stars too widely spaced for collisions, but their gas clouds compressing and triggering intense bursts of star formation. The night sky for any observers in either galaxy will be transformed, filled with new star-forming regions and the distorted shape of the approaching galaxy. Over several close passages spanning perhaps 1 billion years, the two galaxies will lose energy to dynamical friction and eventually merge into a single, larger galaxy. The elegant spiral structures of both galaxies will be destroyed, replaced by the more chaotic orbits characteristic of an elliptical galaxy. The supermassive black holes at the centers of both galaxies will spiral toward each other, eventually merging in an event that will send gravitational waves rippling across the universe. This local drama is just one example of ongoing galaxy evolution. Across the universe, galaxies continue to merge, though at a decreasing rate as cosmic expansion carries them apart. Smaller galaxies are absorbed by larger ones through minor mergers that build up galaxy halos and thicken disks. Galaxy clusters continue to grow by accreting groups and field galaxies, though this growth will eventually cease as acceleration prevents new material from falling in. The long-term future of star formation in galaxies depends on their gas supplies and ability to accrete fresh material. Current star formation rates cannot be sustained indefinitely. The Milky Way, forming 1 or 2 stars per year, would exhaust its gas supply in just a few billion years without fresh accretion. Some gas returns to the interstellar medium as stars die, but much is locked up permanently in stellar remnants. Galaxies that can accrete fresh gas from their surroundings or through minor mergers might maintain modest star formation for tens of billions of years. But cosmic acceleration, driven by dark energy, is gradually shutting down the processes that fuel galaxy evolution. As the universe expands ever faster, it becomes increasingly difficult for galaxies to accrete gas from their surroundings or merge with their neighbours. Galaxies bound in groups and clusters will remain together, but isolated galaxies will become ever more isolated. The cosmic web of filaments connecting galaxies will stretch and fade, eventually breaking apart entirely. In about 100 billion years, the universe will look very different from today. Cosmic acceleration will have carried all galaxy clusters beyond our observable horizon, except for our local group, which will have merged into a single, giant elliptical galaxy. For observers in this future galaxy, the universe will appear to contain only their own galaxy, surrounded by darkness. The cosmic microwave background will have redshifted to undetectably long wavelengths, erasing the evidence of the Big Bang. Star formation will continue at ever-decreasing rates as galaxies exhaust their gas supplies. The most massive stars, those that live fast and die young, will become increasingly rare. The universe will transition from its current state, where stars of all masses are forming, to one dominated by low-mass, long-lived stars. Red dwarfs, the smallest true stars, can shine for trillions of years, far longer than the current age of the universe. The stellar population of galaxies will evolve dramatically over these immense timescales. As more massive stars die and are not replaced, galaxies will become progressively redder and fainter. The brilliant blue stars that trace spiral arms today will vanish. The hot blue horizontal branch stars in elliptical galaxies will disappear. Eventually, only the coolest, reddest stars will remain, painting galaxies in deep crimson hues before they too eventually exhaust their fuel. In approximately 1 trillion years, star formation will have essentially ceased throughout the universe. The last gas clouds will have been converted into stars or dispersed beyond the reach of gravity. The universe will enter what astronomers call the degenerate era, populated not by shining stars but by their remnants, white dwarfs, neutron stars, and black holes. Galaxies will still exist as gravitationally bound systems, but they will be dark, invisible, except for the occasional collision between stellar remnants. White dwarfs, the Earth-sized remnants of stars like our Sun, will slowly cool over timescales that dwarf even the trillions of years we've discussed so far. These cosmic embers will fade from white to yellow to red to infrared, eventually becoming black dwarfs, cold dark spheres of degenerate matter. This cooling process will take at least 10 to the 15th power years, a quadrillion years, a timescale so vast that the universe hasn't existed long enough for any white dwarf to have cooled significantly. The dynamics of galaxies will continue even in this dark future. Stars and stellar remnants will continue to orbit within galaxies, occasionally passing close to each other. These gravitational encounters will gradually evaporate galaxies, ejecting stars into intergalactic space, while causing others to sink toward the galactic center. Over timescales of 10 to the 19th to 10 to the 20th power years, most stars will be ejected from galaxies, while the remainder collapse into the central supermassive black hole. Black holes themselves, once thought to be eternal, will eventually evaporate through Hawking radiation. This quantum mechanical process causes black holes to slowly emit particles, with smaller black holes evaporating faster than larger ones. Stellar mass black holes will evaporate in about 10 to the 67th power years, while supermassive black holes will last much longer, perhaps 10 to the 100th power years. When the last black hole evaporates, it will mark the end of the gravitationally bound structures we call galaxies. But this extraordinarily distant future depends on our understanding of dark energy, which remains incomplete. If dark energy is truly a cosmological constant, the acceleration of the universe will continue forever, leading to the scenario described above. But if dark energy changes over time, the future could be very different. Some models suggest dark energy might weaken, allowing gravity to eventually halt and reverse the expansion, leading to a big crunch. Others propose that dark energy might strengthen, leading to a big rip where acceleration becomes so extreme that it tears apart all structures, from galaxy clusters to atoms themselves. The study of galaxies has revealed fundamental truths about our universe and our place within it, from the discovery that galaxies are island universes separate from our own, to the realization that they're flying apart in an expanding cosmos, to the detection of dark matter and dark energy through their effects on galaxies. These cosmic cities of stars have been our windows into the large-scale structure and evolution of the universe. Galaxies have also taught us about our cosmic heritage. The atoms in our bodies, the carbon in our DNA, the oxygen we breathe, the iron in our blood, all were forged in the nuclear furnaces of stars within galaxies. We are literally made of star stuff, assembled from elements created in stellar cores and dispersed through galaxies by supernova explosions. When we study galaxies, we're studying our cosmic ancestry, tracing the processes that led from the Big Bang to the existence of life. The diversity of galaxies reflects the complexity of the physical processes that shape them, from the elegant spirals with their ongoing star formation to the massive ellipticals that have already converted most of their gas into stars, from the chaotic irregulars shaped by interactions to the countless dwarfs that may be the universe's most common galaxies. Each type tells us something different about how matter organizes itself under gravity's influence. The discovery that most galaxies harbor supermassive black holes at their centers has revealed an unexpected connection between the largest and smallest scales in astrophysics. These black holes, despite containing only a tiny fraction of their galaxy's mass, can regulate star formation across the entire galaxy through feedback processes. This interplay between the microscopic physics near black hole event horizons and the galactic scale processes of star formation illustrates the interconnectedness of physical phenomena across vast scale ranges. Our improving ability to observe distant galaxies has turned telescopes into time machines, allowing us to witness cosmic evolution directly. We can see galaxies as they were when the universe was just a few % of its current age. Watch the peak of cosmic star formation 10 billion years ago, and observe the gradual decline in activity as the universe ages. This direct observation of cosmic history provides tests of our theoretical models and continues to produce surprises that challenge our understanding. The role of dark matter in galaxy formation and evolution remains one of the great mysteries. This invisible substance, detected only through its gravitational effects, appears to provide the scaffolding around which galaxies form. Without dark matter, galaxies as we know them couldn't exist. Yet we still don't know what dark matter is, one of the most profound gaps in our understanding of the universe. Galaxies serve as laboratories for dark matter studies, their dynamics and structures providing clues about this mysterious substance. The discovery of galaxy clusters and the large-scale structure of the universe has revealed that galaxies are not randomly distributed, but organized into a cosmic web of filaments, walls, and voids. This structure, arising from tiny quantum fluctuations in the early universe amplified by gravity over billions of years, shows us how the universe builds complexity from simple beginnings. The patterns we see in galaxy distribution today encode information about the physics of the early universe and the nature of dark matter and dark energy. As we've explored galaxies from their violent births in the early universe to their eventual fade into darkness trillions of years hence, we've seen how these cosmic structures serve as the engines of complexity in the universe. Within galaxies, gas clouds collapse to form stars. Stars create heavy elements, planetary systems form from enriched material, and on at least one small rocky planet orbiting an ordinary star in an unremarkable spiral arm of one galaxy among hundreds of billions. Matter has organized itself into life capable of contemplating its own existence and the galaxies that made it possible. The story of galaxies is far from complete. New discoveries continue to surprise us, from ultra-diffuse galaxies that challenge our understanding of galaxy formation to the unexpectedly massive black holes in the early universe that strain our models of black hole growth. Upcoming telescopes and surveys will reveal galaxies at even greater distances, map the dark matter distribution in unprecedented detail, and perhaps detect the gravitational waves from merging supermassive black holes. As you drift off to sleep tonight, remember that you are part of this grand cosmic story. The galaxy above us, whether visible or hidden by daylight or clouds, continues its stately rotation, carrying our sun and earth along at 230 kilometers per second. We're travelers on a spiral arm of a galaxy that itself travels through an expanding universe filled with hundreds of billions of other galaxies, each with its own history, structure, and destiny. From the smallest dwarf galaxies with just a few million stars, to the giant ellipticals containing trillions, from the violent quasars powered by feeding supermassive black holes, to the gentle spirals where new stars are born, galaxies in all their variety represent the universe's grandest structures, the cosmic cities where matter gathers, stars form, and the elements of life are forged. They are the stages upon which the drama of cosmic evolution plays out, from the universe's youth to its far distant future. As you close your eyes and let sleep take you, imagine yourself drifting through the cosmos, passing by spirals with their graceful arms, ellipticals in their serene retirement, irregulars in their chaotic beauty. See the galaxy clusters bound together by gravity and dark matter, the filaments of the cosmic web stretching across the void, the quasars blazing in the distant universe. You're witnessing the entire story of galaxies, from their emergence from quantum fluctuations to their eventual dissolution in the far future, a story in which we all play a part, made from star stuff and briefly conscious in this remarkable universe of galaxies.